Thank you for visiting our work. My name is Sungmin Kim, a master's student at Inha University in the CVPR lab. Today I will be presenting our study on understanding and improving the adversarial robustness of vision transformers. Our work starts from a simple question. Adversarial training works very well for CNS, but it is harder to make vision transformers robust in the same way. This question matters because robustness research has so far focused mostly on CNS. Only about 13% of robust bench studies target VITs, and the internal mechanism of a robust VIT is still not well understood. So, before designing a new method, we first try to understand where a VIT's vulnerability comes from. To study this, we introduce gradient path masking. Inside each attention block, the gradient flows through three paths: the QK path and V path and the residual path. We keep the fourth path unchanged and simply mask one path at a time during backpropagation to see how much the attack still works. The results are clear. When we mask the QK path, the attack still succeeds, which suggests that the QK path carries the robustness related signal. When we mask the residual path, attack effectiveness drops sharply. This points the residual path as the main vulnerability bottleneck. Our second finding is about what robust VIT learn. In the CLEX activation maps of an adversarially trained VIT, the model attends to the semantic parts of the object rather than only digital boundary. Interestingly, this comes from class level alone without any segmentation supervision. Third, we look at patch associations. In standard training, early layers use both local and global patches. After adversarial training, the VIT reduces its local dependence in the first block and relies more on global relations. One practical implication is that VIT and CNN hybrid, which include a local inductive bias by design, may be more difficult to make robust. These three findings lead naturally to our method. It is a simple plug-and-play two-stage framework built on knowledge distillation. We first train a teacher model, then we distill it into the student using chem distillation, a hierarchical presophthalmic distillation across all layers and heads. This lets the model inherit the semantic priors we observe. We also apply residual gating, a single learnable scalar per block that attenuates the residual path and addresses the bottleneck we identified earlier. The total loss is simply the standard adversarial training loss plus a distillation term, and it works with PGDAT, trace, and MART without modification. In our experiments, the method shows consistent improvement. Across several VIT variants and adversarial training methods, we observe consistent gain in both clean accuracy and robustness. The effect is especially strong on hybrid VITs. We also confirm that the model relies less on the residual path, which matches the goal of our design. To summarize, we identify where the vulnerability lies, studies what robust VITs learn, and turn these observations into a simple and effective framework for improving the robustness of VITs. Thank you for listening.